What if a robot could feel the sting of a mistake before it ever makes one? What if it could learn from consequences, from a kind of synthetic pain, without ever causing any real harm? This isn't science fiction. It's the key to building machines we can finally trust. Because in our homes, our hospitals, and on our streets, the stakes are incredibly high. For robots operating in the real world, choices must be right the first time. There are no second chances when a mistake could mean a dropped patient, a factory shutdown, or a traffic accident. Intelligence alone isn't enough. A machine that can't care about the outcome is just a liability. So, how do you teach a machine to care? You give it something to strive for and something to avoid. We introduce a simple, powerful idea. A tiny digital signal for reward and another for synthetic pain. This transforms cold, indifferent pattern-matching engines into purposeful actors. Suddenly, the machine has a preference. It wants to succeed. It learns to fear failure. Without this, even the most advanced intelligence can get stuck. A person can be brilliant, yet fail to choose breakfast. Without the emotional push and pull of wanting one thing over another, decisions freeze. Early AIs were just like that, utterly indifferent. Shakespeare or nonsense, it was all just patterns in, patterns out. They didn't care about the results. This is the story of how we taught machines to want. It's a journey that starts not with silicon chips, but in 1961 with simple matchboxes and beads, and ends with robots that can imagine the future and learn from their mistakes before they happen. To understand the AI that now lives and works in our world, you need to understand how we taught it to feel the consequences of its actions. At its core, reinforcement learning is a simple, powerful idea. An agent learns by doing. It tries things, gets feedback on the outcome, and over time, figures out how to do better. It's a fundamental process of trial and error, refined by consequences. Think about training a puppy. When it follows a command like sit, it gets a treat. That's a positive reward. But if it chews the sofa, it gets a firm no. That's a punishment. This constant loop of reward and consequence is what shapes its behavior, teaching it what to do and what to avoid. We apply the exact same principle to machines. The agent can be a character in a video game, a trading algorithm, or a physical robot in the real world. For a machine, the feedback is purely mathematical. A good action gets a positive number. A bad one gets a negative number. This is the machine's version of pleasure and pain, a synthetic pain signal that guides its learning. The process has two key parts. First, the agent perceives the current situation, or state. Then, it chooses an action based on its policy, its strategy for what to do in that state to get the most reward, not just now, but over the long run. This idea isn't new. Back in 1961, computer scientist Donald Michie built a remarkable learning machine using 300 matchboxes to teach it tic-tac-toe. He called it Menace. Each matchbox represented a unique board position the machine might encounter. Inside each box were colored beads, with each color corresponding to a possible move. To make a move, Michie would find the box for the current board state and randomly draw a bead. At first, the machine played without any skill, but after each game, he would reinforce its choices. If the machine won, he rewarded it by adding more beads of the colors that led to victory. If it lost, he punished it by removing the beads for the losing moves. Over hundreds of games, the winning colors became more common, making good moves more likely to be chosen. A coherent strategy emerged from this simple, elegant feedback loop. Eventually, the Matchbox machine learned to play a perfect game of tic-tac-toe, never losing. It learned to care about winning, guided only by wins and losses. But this clever method has a fatal flaw: it doesn't scale. For a complex problem like chess or Go, the number of possible states explodes. You'd need more matchboxes than atoms in the universe. Michie also applied this to a classic robotics problem: balancing a pole on a moving cart. He grouped, or binned, the pole's continuous speeds and angles into discrete boxes. It worked, but it was still a coarse and limited solution. The next leap came from an idea by Claude Shannon. Instead of memorizing every state, what if a machine could learn a value function, a way to score any position and simply pick the move that leads to the best future score? It's like developing an intuition, a gut feeling for what makes a position strong. But for decades, the rules for that intuition had to be hand-coded by human experts, which created a hard ceiling on performance. The grand challenge became, could a machine learn that intuition, the features of a good position, all by itself? The journey began simply. In the 1950s, AI pioneer Arthur Samuel programmed a computer to play checkers. Instead of telling it exactly what a good move was, he let it learn by playing against itself, over and over. The program adjusted its own internal feature weights, its sense of what board positions were valuable. After countless games, it developed an intuition that surpassed its own creator. This was a profound shift. A machine had learned a sense of what truly matters in a complex game, not from explicit rules, but from raw experience. Decades later, Gerald Tesoro's TD Gammon took this a step further. It used a neural network to learn features directly from the raw backgammon board, a far more complex task. The key was temporal difference, or TD learning. This method constantly refines its understanding by comparing its prediction for the current move with its prediction for the next. Each move nudges the estimates, and the final outcome, a win or loss, anchors the entire chain of learning, rippling understanding backward through every decision. The result was astonishingly strong, intuitive play, learned entirely, not hand-coded. Then, big neural nets changed everything. DeepMind fused these large networks with a technique called Q-learning, creating the Deep-Q network, or DQN. It learned to master Atari games by looking at nothing but pixels and the score. There were no handcrafted rules, just raw input. It began by playing randomly, but after millions of games, it surpassed human-level performance on many titles. You could literally see the machine's internal value estimate rise as victory approached. It had learned the feeling of anticipation. But for the physical world, this approach had a flaw. Forcing the smooth, continuous actions of a robot into discrete choices made them brittle and awkward. So, researchers shifted from learning the of actions to learning a directly, outputting a probability distribution over a continuous range of actions. An untrained policy is flat, seeing all moves as equally likely. But with experience, it learns to lean into better, more effective moves. The problem? Reality is slow, expensive, and unforgiving. Robots break. Progress can crawl. The solution was simulation, which compresses years of trial and error into hours. But this created a new challenge, the sim-to-real gap. A robot, trained in a perfect digital world, would fail in our messy one. Weirdly, the fix wasn't to build more perfect simulations. It was to build messier, more varied ones, forcing the AI to learn a strategy robust enough for reality. Train across thousands of messy worlds. Randomize gravity, friction, lighting, colors, sizes. OpenAI showed a hand trained in sim could manipulate a block for real. Because it saw variety, it generalized and recovered from surprises. Practice under tough conditions builds robust skills. Beating games was big, but the real world is continuous and unforgiving. NVIDIA, led by Jensen Huang, powers this wave with massive GPU compute. Satya Nadella's Microsoft deploys and scales these systems worldwide. Sundar Pichai's Google pushes multimodal models like Gemini for reasoning. OpenAI under Sam Altman explores agents, memory, and broader learning. Elon Musk's xAI trains Grok with a focus on real-time world context. Across the industry, AGI ambitions, ADS for autonomy, and deep research at Microsoft. DeepMind trains humanoids in randomized sims, rewarding goals. Transferred to hardware, they anticipate shots and block before impact. Complex behavior emerges as smooth paths through action space. The lesson: messy practice plus rich rewards forge robust physical intelligence. Next, robots learn by watching us and by imagining their next moves. Millions of hours of human motion teach a huge repertoire of skills. Before acting, the robot runs a quick mental simulation of outcomes. Like language models thinking aloud, robots think with their bodies. But imagination alone is useless if you don't care about results. Synthetic pain adds that care. Feel failure before it happens. The robot pivots away from danger towards success. Imitation, imagination, and reinforcement close the learning loop. This is not human suffering. It's a simple signal for machines. It powers intuition, adaptation, and foresight in messy reality. We must set careful goals and guardrails as systems grow stronger. To build helpful, adaptable, safe AI, we first teach it how to feel. Feeling, as reward and synthetic pain, is the engine of learning. From GPUs to labs to startups, this is how we go from patterns to purpose. Source highlights: the full history of reinforcement learning, from games to robots. Thanks for watching.